Let's find out. Hello. If there's anyone there, supposedly. Nope. Just want to make sure. Awesome. Cool. 2 minutes. Should be working. Hello there, and welcome to Linear Algebra, here on the Abelian Grouper. Today, I will be your host. Let's just refer to myself as Dear Schley Colonel Sanders for the time being. This channel is all about a couple of things. One of them being, I want to just relearn all the math I've forgotten in the last 5 years or so. Also, I want to help people out there learning this stuff because I think it's pretty rad. And also, maybe at some point it could, I don't know, prove monetary or something. Whatevs. Anywho's. So today, we're going to talk about linear algebra. We begin with fields. And after that, we're going to talk about vector spaces. This was all talked about in the preview. And I'm not being especially clever right now. So let's just go right into fields, shall we? So here's a handy set of axioms. The definition for a field. And it's really just a very nice ring. So in particular, if we look at axiom 1, all that we have here is associativity. Axiom 2, we have commutativity of our two operations. And so on and so forth. And so let's just start with the easiest field, probably everyone's favorite field. And that's the real numbers. And that's just rational numbers with all the holes filled in. Yeah? So let's verify that this holds all the axioms. Well, if you take, let's say, I don't know, how about A, B, and C and R? These are just properties of real numbers that we all know and love, eh? Associativity certainly holds for multiplication, yeah? Right, what this says is if you're multiplying multiple things, the order doesn't matter. Then that's not too surprising, right? Like 3 times 4 times 5. That's what, 60? Yeah? But also, I mean, it doesn't matter if I do 3 times 4 times 5, right? 12 times 5. Or if I do 3 times 4 times 5, right? 3 times 20. So yeah, this holds. The same is obviously true for addition, right? Yeah, I can just bracket it. I can do 7 plus 5. Right? Or 3 plus 9. And it works out the same. It's 12 either way, yeah? So that takes off our first axiom. What do we have next? Next we have to show that this is commutative. This is obvious, right? Like commutivity. This is just a property of real numbers. Yes, yes? So like, you know, if we multiply two real numbers, the order doesn't matter. Yes, yes? Boom. And this is right, like 3 plus 4 is the same as 4 plus 3. And so on, yeah? And the other axioms follow pretty quickly. We have inverses, and we have identities. So fields have two operations, plus and times, yeah? Be a little more surgical here, yeah? And we have to have a 0 that's not equal to 1, and they're both inside this field, yeah? Obviously, just the numbers 1 and 0. And then, well, we also have inverses, right? So if A is an element of real numbers, well, we just take negative A. I mean, that's also in there, right? And if we add those together, we get 0. Yeah. Similarly, right? As long as A isn't 0, then 1 over A is also in there, right? And the same goodness, natural bounty of heaven, wonderful, delicious things. Yes, yes, yes. So that's our field, right? This is the first example of a field. It satisfies all of those axioms and does so quite nicely. It's one of the more commonly used fields. And it's nice because it's a complete ordered field. But there's another field that's also very nice, and that's the complex numbers. These are nice. Right, and this is the set of all x plus iy, that x and y are real numbers, yeah? And the same thing happens. Obviously, we have additive inverses. 1 and 0 are in there as well. They fulfill their same roles. Division, multiplicative inverses are a little more, a bit of work. They're a little bit of work, but we can handle some work. I think, I hope. I don't know. I don't know how it's awkward more the second time. There's also other fields. Q is a field. The rational numbers, yeah. Let's say A over B. With A over B being integers and B not 0. There's a field. C1 the field. Another nice field. You can take the rational functions, say with real coefficients. Yeah, so there's a lot of fields out there. They're pretty cool, I guess. They're really just really nice rings. They're integral domains that have 1, and all the non-zero elements are units, if you want to approach it from a group theory perspective. But that's not what this is. That's what Thursdays are for. This is some primo chalkboard work right here too. So that's fields. The most important thing about fields is that we can always multiply away stuff and get back to 1, and we can always add stuff away and get to 0. What 0 and 1 are will fluctuate depending on where we are, as we'll see here in a little bit. But overall, it's pretty straightforward. Fields, they're just kind of in the background. But they're important. They're there because, as we'll see, switching now to the main topic. We have our vector spaces. These are the main objects of linear algebra. And we have the 8 axioms of vector spaces over there. And as you can see, there's a lot of them. They're not especially exciting. There's a few important things to notice, though, certainly for the problems we'll do in a minute. So, for example, we need the vectors to commute. Right? So let's be a little bit more precise here and look at this definition, right? So V is a set of vectors, right? And F is a field, one of those nice things we just saw. Well then, a vector space, we need a couple of things. We need 2 maps. So we have 2 maps. The first one is what's called vector addition. Yeah, and this is a map from the set of vectors crossed with itself back into the set of vectors, yeah. And in most cases, this is like exactly what you would think it would be, especially if you hopefully, I guess I should say, like, if this is all really weird, I don't know, maybe calculus is a good idea. Whatever. And then we also have scalar multiplication. Sorry, that sounded bad. I'm all nervous and such. Right. And this goes from the cross product, not the cross product, sorry, the direct product of the field and the vector space back into the vector space, yeah. So what does this mean? It means you take 2 vectors. This is gonna, I love that this, I mean, it's typed up over there, I know, but this just cracks me up. It's like, well, we define x plus y. Well, that maps to the new vector x plus y. And similarly, right, you say, well, c times a, well, it's just c times a. I mean, whatever this means, right, these new objects, yeah? But both of these are back in the vector space, yeah? And that's pretty key. Especially when we get into subspaces, this notion of things being closed under addition and scalar multiplication is very key. And in this mind is the key. Mind key, mind key. What are some other good axioms down there? The identities. So here's an important bit of stuff. So we know there's a 0. One thing I want to mention right now is there are potentially multiple zeros. So we have a 0 vector. Yeah. But we also we also have a 0 scalar in the field, yeah. So one thing we have to keep track of is which. So this next axiom here, axiom number axiom. Come on, brain, turn on. Oh yeah, so axiom 4. Yes? So axiom 4 says, right, we need this thing to be in the vector space, yeah. And it has your standard it's the identity, right? It does exactly what you say it should do. I don't want to draw bars all the time, so I don't know. If it's not obvious contextually, we'll make a point of talking about it. Anyway, yeah. So the rest of these axioms, we have an important one, right? We have additive inverses. That's what axiom 6 says. We have the multiplicative 1 in the field. So we have an identity. And then we have these 2 distributive laws. That's pretty standard stuff. All of this, if you've taken abstract algebra, should look very familiar. There's like a vector space is essentially this set V is an abelian group. Hey, maybe that's a Boolean grouper. Yeah, yeah. Fish that commutes. What? And and I just lost my place. Yeah. So yeah, we have an abelian group, and then you create a module over it. Except in this case, instead of using an arbitrary ring, you're using a very nice ring, a field. Yeah. So yeah, so we have this interplay between the field and the vectors, and they distribute both ways. So this is important because, you know, if we have this kind of thing, going back and forth between these kinds of scenarios, it seems very trivial, but it's actually quite useful, and it's a nice bit of trickery, as we'll see in just a minute. But rather wallow in this abstract nonsense, let's look at some concrete examples. So some examples of vector spaces. Any field, say R is your set of vectors, and then just make your field also R. But this isn't enough. We also need two operations, right? Because as we can see in our axioms there, especially in this region, right? We need all these different things, these operations, yeah? We need a vector addition and a scalar multiplication, and we need to find a way to define those things, and so we do it the most obvious way. Just normal addition, right? Like, you just, A plus B is the normal way you would always add two real numbers, right? And then, for scalar addition, or multiplication, it's just, you just multiply two real numbers. So, you know, here's an example of this. I know we know this, right? But still, this is just an example of what's, you know, a special case of this. And then similarly, the scalar multiplication, it's exactly what it should be, right? And you can do this with any field. Let's say V1 is your field, and then, as silly as that looks, the field is the field. So any field will be a vector space over itself. Let's write that down. Bam. Bam, bam, bam. Yeah. So anytime you have a field, oh, I forgot to talk about finite fields. So for example, so any field is a field over of a vector space over itself. So take the complex numbers over themselves, take the rational numbers over themselves, the rational functions over themselves. But there's other times you have to be a little careful. There's also finite fields, which I'll talk about at the end. Yeah. So this is an easy set of examples. And it's, again, because you're just multiplying numbers in the field, the axioms from the field, like just the fact that it is a field, all of the vector space axioms fall out immediately. Yeah. The next set of examples is just the good old tuples. So Rn or Fn or Cn. These higher dimensional vector spaces. So what is this, right? I mean, this is the set of all A1, the n tuples, yeah? the n tuples. Deedly doodly. And then we need a field. And so what field do we use? Oh, I don't know. Well, how about this field? And you have to be careful here. We'll see an example where you can take the tuples from a field, the n tuples from a field, and depending on which field you try to put over it, you may or may not actually achieve a vector space. Yeah? But let's define our operations. So addition, I'm just going to call it VA if that's cool. That's cool. That's wild, man. Whatever. Anyway, so if you have, say, x plus y, or, sorry, let's say a1 an plus b1 bn. Yeah. I mean, the obvious thing to do here is just add component-wise, and that's exactly what we do. Throw an extra one in there for good measure. That works. Similarly, for scalar addition, I'll just call that SAW. In this case, what do we have? So we take some constant, let's say, in this case, it's a real number, or whatever the field element is. Well, then, if we have C times, let's say, A1 to AN, we do the obvious thing, we just distribute the constant across all the components. Boom. Yeah. Pretty standard stuff. And so let's do some axiom checking, eh? So let's start with the easy ones. Is there a zero? What is zero? Okay, let's get rid of this. We know what these things are. But let's ask ourselves, is there a zero? Well, zero, in this case, the zero vector, is just the n tuple where every component is zero. Yes, yes. And also, if we have some arbitrary vector, right, we need an additive inverse for this little fella. Where could we find one? Well, it's exactly what it should be, right? You take the things that are sort of obvious, and this is the most beautiful thing. I used to find linear algebra bland, like stale saltines that didn't have salt. And it kind of is, but it's also really awesome and really powerful. And the best part about it is linear algebra does anything that you would like to be true, linear algebra makes it so. And that's what this is all about, because like, what's the obvious choice? Well, that. Yeah. So there's our additive inverses, yeah? So, and obviously because these are all real numbers, the way we defined addition, that's going to be abelian, right? Because again, we're just adding real numbers, so that's commutative. So our vectors form an abelian group. That's good. It's very easy to see. Let's check the distributive properties real quick. They're not hard to check. So let's suppose that A and B, let's just stick to Rn. Rn. Let's say our field R, and let's let X and Y be in Rn. Boom, chicka, boom, chicka, boom, chicka, boom. So what do we need to show? Well, we need to show these guys down here, these last two axioms, yeah? So what do? So let's show that if we have A plus B times, let's just say X. I guess I just switched those up, didn't I? Whatever. Okay. Well, so this is from the field, right? Because these two things are in the real numbers, so their sum is in the real numbers. So this is just a field element, and we know by our definition of multiplication, we just distribute it across. Yeah? And then, well, what would we do here? So x1 in this first component, this is just a real number, and these are all real numbers, and we know that the distributive property holds in real numbers, so this just distributes. Yes, yes? And now if we're clever, we'll remember the fact of how we defined addition for these, and we'll just undo this addition component-wise, and we'll get a x1 a xn plus bx1 bxn, which is precisely, right, so we need to show that this is equal to, well, what is this? This is a times x, right? I'll write them out. And this is b times x. Boo! Huzzah! And that's what we wanted to show, yeah? The other axiom is left to the reader as an exercise. Yeah. So yeah, so those make a nice collection of vector spaces. Let's do a couple others. Let's knock out like two more really big ones. And then we'll prove a theorem. Maybe two theorems. Whatever. Anyway, so another really important example, in fact, you could say it's sort of it's one of the motivating examples of the whole subject, is are the matrices. With, what do you call them? Let's say components from a field F. And of course, in general, in life, you don't have to have your matrices come from a field, but I think for our purposes, we definitely want them to. So, yeah. In particular, so what is a matrix? Well, it's a rectangular array. M rows and n columns, where components are denoted. So, if we have a matrix A, so let's say a matrix A, right? It's one of these things. Yeah. And so we denote the component, right? So these things are a two-dimensional thing, right? They have latitude and longitude, or however that goes. And so we need two coordinates to identify each little fella in there. And so first, for I, this is the ith row and the jth column. So for example, if we had a matrix which unfortunately no one can be told what it is. You see it when you take out your garbage. Wait, oh, that was Hugo Weaving. I totally did that backwards. Even help your landlady take out her garbage. Whatever. Anyway, so here's a matrix. Let's call this matrix A. So, for example, A1, 1, that's the component in the first row and first column. Ba-doing. That's 2. A2, 2. Second row, second column is 1. Probably seen matrices before. And so we have a set of these things. Now that we sort of know what they are, let's say let me write this down. So what is this thing? This is the set of all m by n matrices with entries from the field F. Whew. Yeah. Cool. So there's our set, and now we need operations. So let's say if A and B are in this set, we'll define A plus B. We'll define it in terms of this little component-wise thing that you can still kind of see there. So it will be exactly what you think it should be, just component-wise, yeah? So let's do a really easy one. Yeah, so we just add components. So 1 minus 1 is a goose egg. 2 plus 3 is 5, minus 1, and 3. Yeah. And obviously, so we could go through all the axioms, but I think you should do that. Also, but the thing is, we can hand wave because if we think about the field axioms again, right, like all the distributivity and all the commutivity and all that stuff's going to work because since we're doing this component-wise, everything is just going to be added. There's just field elements being added. And because they're field elements, all that stuff naturally works. So our addition is exactly what you think it should be. Similarly, you have a constant from the field. In the west wind moves on the field. Then you do exactly what you think you should. You just multiply each component in said matrix by that constant. So if you had 3 times the matrix 1, 1, 0, 1, Mr. Anderson. Then you just multiply across, yeah? And again, you know, if you have this sort of thing, well, what's going to happen? I mean, everything's going to distribute inside these matrices because all of the components are from the field. And because the components are from the field, everything works. Yes, yes, yes. It's our time. It's flying. Yeah, 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 yeah. So we're going to spend a lot of time with matrices. A great deal of time. Cool. Let's do one more. Let's talk about two different collections of vector spaces. Well, they're really just one, but and that's the polynomials. With coefficients from a field, Mr. F. Well, so from this field F, right? So, what are these things? These are the things that look like this. Do you look like I do? Let's go descending. You know, an x to the n, an minus 1, x to the n minus 1, a 1x, a 0. That's really poor board management. It's from all those years being under the toil of having to use dry erase boards. Anyway, so here's a polynomial. And so let's define, so there's two different notations for it. This is a more like abstract algebra notation. You can also say this notation, polynomials over some field. And what it is just the collection of all those. I don't want to write all those words out again. Yeah, so it's a collection of all the coefficients. Yeah, so it's polynomials with coefficients from the field, and you put all of them together. And that forms a vector space. What do you think the 0 polynomial is? Oh, shoot. I just gave it away. The 0 polynomial, let's call it Z. Well, it's just 0, right? Because remember, polynomials include constants. So all the constant functions are considered polynomials, and one of those constant functions is the 0 function. So strictly speaking, this is the 0 function. Not the number 0. Because all of these are functions, yeah? Polynomials put the fun in function. I'm glad I can't see if, like, whatever. So, and then again, so let's at least define the operations here, and then I think this will be another exercise for the reader. I mean, I'll define just by way of an example. You know, if we had 4x to the 4th plus 3x squared plus 5, right? Let's say this is p of x, and q sacre q is 3x cubed minus 2x squared plus x minus 5. So how would, well, you guys know this. This is like high school algebra stuff here. So vector addition is exactly what it should be. You just group like terms, yeah? So we got 4x to the 4th plus little parentheses here to really make this stand out. So it'll be 3x squared. Oops, I should probably 3x cubed, sorry. And then here we have 3x squared minus 2x squared, so that's just that. And then continuing, we have plus x, and then 5 minus 5 just gives 0. So we're left with 4x to the fourth plus 3x cubed plus x squared plus x. Is this? Do me a favor and double it. Boom. The important thing to notice here is that we get another polynomial. And no matter how many times you add together polynomials, you'll never get anything that's not a polynomial. So this addition is good. It's obviously associative, again, because it's all going to come down to the fact that the coefficients are from the same field. So the field axioms will just push all that through. But you, the reader, this is an opportunity to flex your skills and combine phrases in ways that don't make sense. But here's, to show that, so, okay, well, I guess I should define that. The scalar multiplication. So here's the addition, it's the standard way. And the scalar multiplication, again, it's exactly what you think it should be. So if you have some constant from the field, right, and p of x is some polynomial from, I'll do this notation just because it's more linear algebra-ish. Then c times p of x, right? So p of x is some polynomial, so it's something like an x to the n plus a1x plus a naught. And so what do you think you do? We distribute. Distribute. There's my impression of the Who if they wrote the song Distribute instead of Substitute. Roger Daltrey's like, dude, that was awesome, mate. And again, because C is from the field and the coefficient A of A sub n is from the field and all the coefficients, their products will be in the field. And so when you multiply this thing out, the product of this stuff will be back in the polynomials again. So it's closed under scalar multiplication. And the rest of the axioms I will leave up to you to check. Sweet. Sweet, sweet. Now let's prove a couple theorems, and then we'll call it a day. Let's do it. So, we'll come back to those if we need them. We may need them. Boop-a-doo-boop-a-doo. Problems. So I typed these up the other day. I'll post them somewhere soon. But let's prove number 2. So let's let V be a vector space. And here we don't, if it's, I realize I just rushed through all this vector space stuff, and if you've never seen one before, it's probably kind of weird, but I think doing stuff like this will help us see what these axioms mean and how they're useful and so forth and all that. Anyway, so let's let V be a vector space. I'm just going to call it a VS if you don't mind. And let's let, I don't know, how many do I need? X, Y, and Z. This is Z's chopper, and Z is dead. So we'll take 3 vectors, and what do I need? Just 1, that's it. So let's prove the cancellation law. I mean, this is almost trivial. So what that says is that it's actually not trivial. No, I take that back. So if we have x plus z equals y plus z, then yeah. So what are we going to do about that one? So what do we need to do? We need to show right? And this isn't surprising, right? I mean, like, your intuition is like, well, yeah, just subtract z, or yeah, z from both sides. All right, but strictly speaking, I mean, we want to do this at least somewhat legit, so let's do it. How do I start? Is this really the one I wanted to start? I guessed it. How should we start? How should we start? Well, let's see. So we know that, let's just see if we can do it. Let's just wing it. So what do we know? We know that these two things are equal. We also know from the, so let's do some scratch work before we write out the solution here. So let's do scratch work before we try to write a nice little proof. So okay, so we know that those two things are equal by assumption. We also know that there exists yeah. Should I actually, sorry. Space cadet. Well, let's just see if we can figure it out. So, so what do we need to do? We want to show that this is true. So what we do know is that because this is a vector space, that there exists a, let's call it a negative x in V, right? That's such that x plus negative x equals 0, right? Yes, yes. And why is my brain failing me? What else could we do? Come on, brain. Come on, brain. Deep, 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 deep. Deep, 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 deep. Gonna look at my notes real quick. Gonna look at my notes real quick. Yeah. Oh, okay, yeah, that's right. Look at my notes real quick. So let's actually, I'm gonna change it actually. Let's just do this just so I can keep it in my head. Right? Just for y. So let's just do something that seems weird. Like x does equal x plus 0. Would you agree? You'd be surprised how useful adding 0 can be in mathematics. We'll see that quite a bit if you pay attention to this channel, and you'll. Anyway, so if we do that, well, we know that this is true, yeah? Because this is a vector space, we know there's some vector in there that I can add to y and get 0. So that means that I'll just substitute in. Substitute! So x plus y minus, well, let's do it this way, plus minus y equals 0. Or no, sorry. That still equals x, silly. Yeah? And now, let's reassociate. I need some more room here. Yeah, let me just rewrite the whole thing. It's all coming back to me when I add 0 like this. And then I substitute y plus y inverse. Then I know we can reassociate, yeah? Because that's one of those 47 axioms for a vector space, is that we can add these in different orders. So x plus y plus minus y, yeah? Wait, why is that helpful? Back to the notes, back to the notes, back to the notes. Oh. Alright. Yeah, I don't know. If anyone's watching and they commented about what to do, I just realized this is the thing we want to fiddle with. Not x or y. We need to fiddle with this. So we know there's a negative z in our vector space. Yeah. So this is the one. Third time's the charm, hopefully. There we go. It's all coming back to me now. Boom. Okay. Now we're good. Because now I can do something else. So we have this x plus z. Well, by assumption, we know that's the same as y plus z. That's just by assumption. Yeah, so then we'll get, this is the same as y plus z plus minus z. Isn't this awesome? Don't you love when, like, adding 0, then we reassociate again? Yeah. There it is. That's 0. And by assumption, right, this is one of the axioms. If we add 0, we get the same thing. So x equals y. Whew! You know what's cool is I inadvertently, like, all the scratch work went away, like, exactly when it was supposed to. I gotta stand closer to the board so the focus stays on it. Words and phrases. So that first one holds, right? 2a is proven. Now let's show, the other two are way easier. Especially this 0 one. I love this proof. You have to do this, like, usually in group theory too. Like if you take a group theory class, say Thursday night group theory, starting tomorrow. You always have to do a proof like this. So let's show that the 0 vector is unique. Right? Because strictly speaking, the axioms only say that there has to be a 0 in there. There's nowhere that it says it has to be the only one. But let's show that there is in fact only one. It destroyed all the other people from the planet. Yeah. There can be only one. There can be only one. I know everything. Anyway, so let's show it's unique. So let's do a contradiction proof. Let's suppose not. Or no, rather, let's just suppose there are two. So let's suppose that 0, let's call it 0a, and 0b both satisfy right, they're both identity elements. Yeah? So what we want to do is show that they're the same. So we want to show that 0a equals 0b. And that way, like, anytime you have a 0, you know it's the only one. The only one there could ever be. Oh, yeah. Anyway, so this is so ridiculous. So we'll do, well, okay, 0a is equal to 0a plus 0b because by assumption, this holds, right? This holds for everything. So in particular, it holds for this thing. Yeah, because this is an identity by assumption. But also by assumption, this is an identity. So that's it. Yeah. Easy peasy. Lemon cheesy. I'm so old. Okay. Finally, the other one. Let's show that that additive inverses are unique. It's more of this silly trickery. So again, let's suppose. So let's let we'll let V be a here. We'll let V be a vector in our vector space, and we'll let negative V1 and negative V2 be inverses of V. So what does that mean? That means, so we're assuming that both V plus negative V1 equals 0. Right, and it works both ways. Yeah. That's the one, Marv. That's the silver tuna. What could we do? Yeah, this one's pretty trivial too, actually. I mean, let's just write these down because they're equal to each other, right? So, I mean, there's almost nothing to do. So if we take, say, V plus minus V1, that's equal to 0, which is equal to V plus minus V2, yeah. And we proved in part A that we can cancel. We have the cancellation laws. So let's say by part A, yeah, negative V1 equals negative V2. So that means they're unique. Inverses are unique, right? Any time you think you have two inverses, they're the same. What do we got next? Should we do 3? Yeah, let's knock out 3 and then call it a night. And I'll post the rest of these questions so that you can, on your own, enjoy the magic of linear algebra while the next week progresses. So let's see. How about number 3? It's a magic number, I'm told. Oh, baby. So number 3 is more of this same silliness. Show that 0 times V. So this is again where this is a good one to finish too, because these kind of things illustrate sort of the difference between the zeros. You gotta go from 0 to hero. So let's show that 0.v equals 0. So here we'll say 0 is the field element, right? And we'll do this bar. That's our 0 vector. And so we want to show that for little v in our big vector space, we want to show that 0 times v equals the 0 vector, which is exactly what it should be. And so let's see. All right. So we're going to use a bunch of stuff here. So let's say, so let's prove this. So 0.v, but I'm not going to start with that. Let's start with 0.v times, or plus 0.v. Well, we know by one of the vector space axioms that we can factor out this 0. Well, both of them, really. The v, I should say. So 0 plus 0 times v. Yeah? But these are just two zero. This is 0 in the field, so 0 plus itself is just 0. So this is 0 times v. Let me not use that notation. Keep consistent here. And then I know that the 0 vector is in my vector space. And I know that if I add the 0 vector to anything, it doesn't change anything. So this is the same as 0.v plus the 0 vector. And so what does that tell us? Well, that tells us that 0.v plus 0.v equals 0.v plus the 0 vector. And how do we take it home? Take it to the bridge! How do we finish? Exactly what we did last time. Cancellation laws, right? We proved that. That's why it was like the premier theorem that we proved in today's exercise. We can use the cancellation laws. We have 0.v equals the 0 vector. Pretty standard stuff. Good stuff though. Quality, nutritious, full of vibrance, goodness. Okay, I'll leave part C as an exercise. Well, we'll see. We'll see. Sweet. Skibbity-boo-boo. Right. So part B is actually a little more interesting. So we want to show that minus C, make sure you get the order right here, times V equals minus CV equals C times minus V. Yeah. Right, where, so we'll let C be in the field and V be in the vector space. Go out into vector space. So let's talk about, these things are actually different objects here. So this, right, V is just the plain old vector. Here we're multiplying it by the scalar negative C. This is C times V. This is the inverse, essentially, of C times V, right? It's exactly what that is. It's not essentially, it's precisely. And this is V inverse times C, right? And we want to show that all of these are equal. Essentially what we want to show is that you can, like, negative 1 times x is negative x is kind of a good thing to do. So what do we know? So by definition, because this is the inverse of C times V, we know that C times V plus this thing wait, did I do that? Whatever. Yeah. I guess I should put that in a box there. There we go. That's better. Right. The important thing, though, to know is that this is unique. Right? And we proved that a minute ago. It was like the last thing we did, I think. Yeah. And this uniqueness is going to be huge. So if we can show that, for example, say, I don't know, say that this thing plus this thing equals 0, then we'll know it has to be equal to this because of the uniqueness of the inverse. Yeah. And similarly, Garmanar. So let's start with let's show that minus CV, let's do this one first, equals minus C times V. I think I used A's on there. Oh, no, I did use C's, cool. So what do we want to do? We want to show that this is the additive inverse. Want to show that this is the additive inverse of CV. Because if this is the additive inverse of CV, we know that inverse is unique, so it has to be equal to that. So what do we want to do? Let's add this thing to CV and see if we can take Walter Sobchak's advice and mark it 0. Sorry. Entering a world of pain. You're like, yeah, this video's been a world of pain. Anyway, so let's well, there's only one thing to do. We'll use that distributive property, right? This is from the field, this is from the field, and this is the same vector. So we know that this is the same as C plus minus C times V. Well, I want to show that's true, yeah? I haven't shown that yet. Getting ahead of myself. We know that this is true, right? Because I can just factor that out. But this is the additive inverse in the field of this, so these combine to be 0 in the field. And as we just proved a minute ago, that's the 0 vector. So because this is the 0 vector, by the uniqueness of inverses, negative CV equals negative CV. Boo, ba doo doo, boo, 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 ba doo. Bam, 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 bam. Right? All right. Hold on. Just one more hold. Okay. So that one's good. Now we just have to show the other inequality, which was this one. Yeah? And I really want to do that one. Yeah. Oh yeah. So we'll finish this, and then this will be the last one we'll do. So we proved that this is true, right? So what we're going to use this fact immediately, and in particular what we'll use, I'm going to write it down before I erase it, circle it in this box. So we just proved this half, right? We know this is true. So this holds for any field element. In particular, it holds for 1. So that means that negative 1 times V equals negative 1 times V. Yep. So let's do it. Let's save that fact. Let's finish this proof, and then we'll call it a day. Cheating on my notes because I'm tired. I'm broken in particular. So let's look at A times, let's look at C times negative V, right? Because this is now the one we got to show. We got to show it's equal to those two. Well, we're going to use this fact. So C times negative V is the same as C times negative 1 times V, right? And then by associativity, right? This is in the field, this is in the field, and it's one of those multiplicative associativities from the vector space axiom. So C times negative 1, which is just negative C from the field stuff. Wait, what am I doing? Let's just reassociate first. I'm getting way ahead of myself. I'm super tired to say silly things like that. So C times negative 1, and now, yeah, just whatever. Negative C times V. But we know that that's equal to that, so this is equal to this is equal to that. And we draw a square, and we say Q-E-D, Q-E-Dizzy, Q-E-Dizzle, for show. Cool. Well, I don't know if anyone tuned into this or not, because I was staring at the board the whole time. But if you did, thanks for tuning in. Tomorrow night we start group theory. And then Monday is like rocket science for beginners. Tuesday we're back to Calc 2, and next Wednesday, subspaces. Thanks for watching.